Okay, so this is like slide 48. So 72 are the ones we've done already. So maybe I'll get to the end of what we've done in this video. So Pythagorean theorem, you all know, right triangles, a squared plus b squared equals c squared. Okay, don't forget that. Pythagorean theorem, very important. Special right triangles. These are on the reference sheet. So this is on the reference sheet. Now, I don't think the state test really cares about special right triangles, but they're on there. All right. So 45, 45, 90, and your 30, 60, 90. They're on the reference sheet. So just know how to use them. And I showed you that in the first video where the reference sheet is, or the formula sheet as they call it. Okay, trigonometry. These are also on there. Right? Remember, that's just your basic SO, CA, TOA. But the picture's not, all right? So that's the problem. So again, when you do this, identify the angle. So they're using A as the angle. So then the side across from it is called the opposite. If that's the right angle, the side across from the right angle is the hypotenuse. And then the third side is the adjacent. And the abbreviations are sine of A, cosine of A, tangent of A. Those are your abbreviations for the words. Again, make sure you're in degrees, right? Don't forget that. Degrees. Big deal. That's the wrench in the calculator. I don't know if they'll ask you this, but inverse, you need to use inverse to find angle measures. So again, you set up the problem just like you are, but if you're looking for the measure of angle A, say you're going to use inverse sine, right? So here's A. So opposite, hypotenuse, adjacent. So katoa. So say you don't care about you don't care about the adjacent. Say you care about the opposite hypotenuse. So you're going to use so. So you would do inverse sine of the opposite side over the hypotenuse. Okay. Now, one thing I forgot in the other slide, and let me just use this picture to do it so that I don't have to go back, all right, is this idea of complementary angles. In this picture, angle A and angle B are complementary. They add to 90 because this angle is already 90 degrees and the triangle adds up to 180. So that means A and B add up to 90. You need to know that the sine of A equals the cosine of B and that the cosine of A equals the sine of B. Remember that. Memorize that. Okay? Just memorize that. The sine of A equals the cosine of B because the sine of A in this picture, the sine of A, is going to be A over C. And the cosine of B is also going to be A over C. And it's again this idea of the adjacent and opposite switch based off of what angle you're looking at. Okay? So be aware of that. That's a gimme question. You'll see that in your practice tests. They like that question for some reason. Application here, angles of elevation and depression. Remember, they're always formed by a horizontal and a line of sight. So that's how you get your angle of elevation. To get your angle of depression, again, this is the weird one. You have to draw that horizontal in the air and your line of sight. And don't forget that the angles of elevation and depression are congruent because they are just alternate interior angles because your horizontals are parallel. Okay, so that's chapter 8. Okay, chapter 9, we're getting into our transformations. So the first talk was on rigid motions. Remember that rigid motions keep your figures congruent because they preserve angle measure and they preserve distance. Now, the first image is called the pre-image. The second one is called the image. So remember that if they use that. So in this picture here, notice that we use the prime notation for the image. So this is your pre-image, triangle JKQ, and this is your image, triangle J prime, K prime, Q prime. Here's how they show the mapping. Remember, this should be a capital J. I don't know why it's not. Typo. Okay, and again, remember that you need to name it in corresponding order, corresponding points. So your first rigid motion is a translation, and remember, a translation is just a slide. So you're just sliding the figure. Again, they stay congruent. In a coordinate plane, you might see this notation. So again, the first is the X slide. Positive means to the right, negative means down for the Y, because the second one's the Y. So notice in this picture, we're going right 4 and down 2. Just slide all the points. For a reflection, remember that if you're going across a line, this line is the perpendicular bisector between the pre-image, and the image, right? Perpendicular bisector. Again, it's a rigid motion, so your figures should stay congruent, uh, pre-image to image. And then here are your rules. These are your common reflection rules. You might want to try to memorize them if you can. It just might be easier. Rotation is the last rigid motion. Again, remember, for rotation, there is always a center and a degrees. So when you connect your pre-image to your center of rotation to your image, you should get that angle of rotation. It should be the same distance away from the center of rotation. Remember, we typically go counterclockwise. Okay, they should state it in the problem, but if they don't, think counterclockwise. Again, here are your rules for rotations in the coordinate plane. And again, it might be a good idea just to try to memorize these. Okay. So that's it for your rigid motions. A dilation is not a rigid motion. The reason is because you have this scale factor, which is going to enlarge or reduce the figure. Now remember, you can find the scale factor a couple different ways. So if this is my pre-image, so the distance from your center of dilation to the pre-image and the distance from your center of dilation to the image should equal out to the scale factor if you take the image and divide by the pre-image. You can also use a pair of corresponding sides. So in these two pictures, if you use segment PR and segment lag, and segment there it is, P prime R prime, to find the, let me pause for, okay, I think that's better. To find, give me 1 second. Okay, so I hope I didn't lose you. Good. I don't think I did. So again, sorry about that. Love technology, sometimes not. As I said, you can find the scale factor using the corresponding lengths to the center of dilation. You can also find the scale factor by taking a pair of corresponding sides. So the image P prime R prime over the pre-image PR. Okay. All right. So again, if you look, these two figures will be similar. So dilations create similar figures. And again, it's this idea of scale factor. All right. And again, here's the picture that I just talked to you about, where you could just use the corresponding side lengths. And again, an enlargement when your scale factor is greater than 1, a reduction when your scale factor is between 0 and 1, all right, less than 1, but a positive number. Okay. So again, a dilation is not a rigid motion. And again, the rule for a dilation is you simply take the original coordinates and you multiply them by the scale factor. Okay, in area, you will have some formulas on the reference sheet, but the one thing I want to talk about is similar figures. Remember that if your similar figures have a scale factor of A over B, then the ratio of the perimeters will still be A over B, because